Okay, so now let's we have a list of special forces and generic forces. Now let's see, how do we analyze, if I give you a situation, how do I analyze all the forces that's present on a body, on an object, right? So let's look at a couple of very typical, very classical examples. One of them is almost a meme at this point. If I have a block on a slope, right? I put a block on a slope. What are the forces that are on here? Now I'll give you a foolproof way to analyze so that you will get all the forces. Some of the basically the biggest mistake, or the biggest mistake students make with doing these type of problems is they either suddenly invent a force that isn't there, or they miss the force that is there. All right, it's very common. I've seen people invent forces that does not exist, right? So I'll show you exactly how it's done. So I'll give you some simple examples, and we'll work up to a couple of harder ones. Okay, we'll do around 5 different examples. So this is the first one. Now the foolproof way that I'm going to show you is this. Ask yourself 2 questions. Okay, ask yourself 2 questions. First, what's touching the object, and secondly, what's not touching the object? What's touching it and what's not touching it? Okay, sounds a bit weird. What that means? Well, what does that mean? The first is simple. What's touching it? What is in contact with it? It sounds a little bit wrong, but that's simple. Understanding what that is. The second question is what's not touching it yet still giving it a force. Okay. Let's look at the first one first. We have a block on a slope, right? What's touching it? What's in contact with it? Well, the slope itself over here. And what does that do? The slope, remember, which one of these, and if it's in contact, you must pick one, right? Which one of this will do it? Did I even have it here? Probably didn't. The reaction force, I think I erased it. Reaction force. Right. And it's exactly that one, right? So you have a slope and it's touching it over here, and you have a reaction force, and it's always normal to the surface of contact, as we said. So if the slope is, if the block is on the slope like this, then the slope will create a force that is normal to it. Now, what we're going to do is draw it in a very specific way. We're going to draw what's called a free body diagram. And called FBD for short. What that means is we will draw the forces as an arrow, right, from the center of mass of an object that we're interested in. Okay, so if this reaction force is by the slope on here, which way does it pushes it? It pushes it this way, right? So it reacts to the body this way. If this is the contact, it's always, remember, reaction force, sometimes called normal force, because it's always normal, or AKA perpendicular to the surface. All right, so let's call that N. We'll put a label here so you remember what we're talking about. Okay, what else is there? What else is in contact with the block? The block is our object of interest on something, or that's the thing. We don't care about what the forces are on the slope. It's just there. I don't even have to draw the full slope. I just need the object. Well, nothing else, right? Can you see? Nothing else is in contact with it. So we're done with the first question. That's the only contact force there is. And then we ask ourselves, what is not touching it, yet it will still produce a force? Well, there's gravity. And now let's ask ourselves, is it relevant over here? Well, yeah, why not? Unless there's a good reason for not counting it, which sometimes there is. For example, if you're in space, or like away from planets, or in other examples that we'll show you, then it should be relevant. So gravity, good. So we start again, draw the arrow from the center of mass of the object. In which direction? Well, the gravity will pull you straight down. So we will give it a name. Let's say G for gravity, like that. Okay, and that's it. Okay. However, I have kind of made a simplification, is that we kind of ignored one of the typical things we do ignore in physics, which is friction. right? So if we ignore friction, that's it. If we do include friction, that means the surface over here will sort of drag it back because there's a tendency. Remember, if you look back in your notes, what do we write about friction? It's the contact force by the surface that opposes either motion or tendency of motion. So if this is sliding down, right, there'll be a friction sort of slowing it down, dragging it back. If it's sort of just staying there, the tendency is for it to slide down. As you can see with these two forces, one is pulling this way, one's pulling this way, it'll kind of pull it down, right? So there must be a force that's going this way. Let's use little f, right? So big capital F, maybe we'll refer to some generic forces, but we'll use little f for friction. So this would be the complete free body diagram. So this is a good point to clarify one thing. So a free body diagram is a diagram that accounts for all the forces present, but it is a very specific way of drawing it, as you can see, right? It starts from the center of mass of the object. And a lot of textbooks take a lot of liberty about this and draw it wrongly. I'll tell you why, right? So there is free body diagrams and there is what I call physical diagram. So a lot of textbooks are actually drawing a physical diagram, I think, including the one you're using. But that's not really an accurate free body diagram, and it will cause a lot of confusion when you're doing the math. The simple way is actually do it properly. Okay, I'll show you what I mean. Is if I push a block like this, I push it to the right, a lot of textbook would draw it like this. Right? It'll draw it by it'll draw it from where you are actually pushing it. But a free body diagram always has the forces starting on this, on the object, like this. So you would draw the pushing force, let's call it P, right? This pushing force to the right. So that's what I consider a physical diagram, and this is a free body diagram. In some sense, a free body diagram actually doesn't even care about the object. It just cares about what are the forces on the object. So if you like, you can just draw a dot to represent that object. However, that becomes a little bit abstract. So sometimes we just put in something with a extent so that you can visualize it a little bit better. But the key difference, right, to make it a free body diagram, and I think if you don't draw it from the center of mass, technically it's not called a free body diagram. You can call it a physical diagram. We won't really deduct any points in an exam, but trust me, a lot of mistakes are led from students insist on drawing it that way instead of this way. This will reduce a lot of mistakes, right? So all arrows must begin at the center of mass of the object. Okay. So this is a feature of free body diagrams, okay? Right, so let's see a couple of more examples, right? Let's have another one. And this is often a confusing one, right? So let's say I toss a tennis ball halfway through, right? So you hit a tennis ball and it's going to following sort of a parabola trajectory. So let's say halfway through here, right? We have a ball over here. Can you draw all the forces on there? So we're going to draw a free body diagram. So all the forces will start from the center of mass over here. Okay. What are the forces over here? So this is a classic example of it's very easy to invent a force that's not there, and you put it in. Right? A lot of students would go like, well, there's probably immediately there's gravity, right? So students would understand, and then they'll go like, okay, the ball's going that way, so there must be a force going that way. Okay, and that's wrong. All right, let's see why is it wrong with our recipe of doing this, right? So let's go back to the ball itself and ask what's touching it, what's in contact with it, right? Well, there's air. What does the air do? The air would create air resistance, right? So it will slow it down. Okay, well, let's not worry about that first because it's really small. Because imagine tossing a tennis ball. Does it really slow down that much? Not really. It does a little bit, but let's keep your life simple. Ignore air resistance, as we'll do many times in this course. All right, ignore air resistance. So, all right, what else? Nothing. So is there any contact force? No, 0. So there's no contact force whatsoever on the tennis ball. So you move on to the next question. What's not touching it? It's a fine print, right? What's not touching it yet still providing a force? And we know there's only gravity. And is it relevant here? Yes. That's all there is. All right. So now it creates a little bit of mystery. Why is it going forward, even though the only force is going down? Well, we'll look at that in the next couple of videos. But that is the correct free body diagram. So practice drawing this, right? Ask yourself what's touching it and what's not touching it, and you always get it correct. Okay. Let's look at a third example. Is this. So let's say I have 2 blocks this time, one small, one large, right? And I'm going to push it. I'm going to push this one, okay? Now, there's 2 objects of interest now, although I can consider them as a system, so 2 together as a collection and almost hide where they're contact and just think of it as one big block. But let's not do that. Let's actually analyze them individually, one at a time, all right? So let's look at a big one. In fact, let's look at a small one first. What are the forces, all right? So again, I'll tell you what is a common mistake. A common mistake is they'll go like, oh, you're pushing it. Okay, so let's draw everything from the center of mass, right? So, well, there's a pushing force this way. And then is there gravity? Well, yes, so there should be gravity. Let's say this is on the floor like that, right? So there's gravity, all right? What else? There is, so before we go in gravity, we should ask what's touching it first. But there's a floor like this because otherwise gravity will sort of pull it down. So there must be some sort of normal force or reaction force pulling it upwards. So that's what's a common diagram students would draw. Can you see what's missing if you use our recipe? All right, let's analyze it carefully. But what's touching the smaller box? Well, my hand is, all right. So that gives a pushing force. That's correct. The floor is, okay, so that's correct. Floor is, so that would provide a normal force. That's correct. But can you see what's missing? Your hand's touching this, it creates the P. The floor is touching this, it's creating the N. Let's not worry about friction at the moment. We'll ignore all friction unless I say so. But there's also this side, right? The big box is touching it. So there's another contact force that's pushing it this way. So any time you have a surface, there will always be a normal force. Okay, it's a bad habit to use the same symbol for 2 forces, so let's differentiate it. Let's call this the normal force from the box B. Okay, so box A and box B. This is the normal force from the table or from the floor. All right, we'll not worry about any subscripts like this. Okay, so there's 4 forces, and this is the one that is often missing from students. Okay, so let's recap, right? So what's touching it? Your hand. It creates P, the floor, which creates N, and this side, the bigger blocks, which will create NB like this. And then you move on to what's not touching it and gravity. So you have gravity over here as well. So these are the forces that are exerted on the smaller box or box A. All right. What are the forces on box B? So this is a common example of students. A very common mistake of students will forget to include a force that is there. And let me give you an example of students would invent a force that is not there, right? So they put in an extra force. So I'm just copying B out, right? So I'll draw all the forces on B here. In fact, let's not even draw the ground. I'll just draw B, right? And draw the free body diagram for B. For B. This itself, if I remove everything, but even if there is something here, it's fine. Free body diagram for A. So what are the forces on B? Okay. Well, I'm pushing it from here, right? So this is a common mistake that students would go like, oh, there's a pushing force from the hand, and then they'll draw something else, right? But let me ask you, is that force even valid? And to answer that question, you should ask, is your hand touching the box B? No, your hand is not touching it. So your hand does not exert a force on box B. That should not be there, right? So that's an example of students missing a force that is there from here, but that's an example of students inventing a force does not belong to B. The hand only pushes A, okay? Now, what is the correct way? Well, the correct way is over here. That's in contact with the smaller box, right? So here you will have a pushing force. In fact, since it's sort of a surface, let's call it a normal force. So you have a normal force from A, right? So let's for now put in more subscript explanations from A on B, right? So to clarify, this is from B on A. And what else is touching it? Well, the floor is touching it. So you will also have a normal force, okay? Because we have a lot of different types of normal force. So let's clarify it. This is the normal force from the floor on B, okay? What else is touching it? What else is in contact with B? So we have this side, nothing else, and that's it, okay? So, now you ask what's not touching it to complete your story. What's not touching it and still exerting a force? Well, gravity, right? So you should put gravity here. Again, I tend not to, trying not to use the same symbol for two different forces. This is a gravity on A, so let's put it like this. Let's actually, so you can call it GA and GB, or if you like, you can call it G from Earth on B, and this is G from Earth on A, right? So you can simplify it as GA or GB like this. So in summary, how many forces are there on A? 4. Okay. How many forces are there on B? 3. Okay. So the mistakes often come with students might think there's an extra force because you're pushing it, right? So there's a pushing force from the hand on B, which is not correct. So never include that force. So the mistake is a common mistake is including that and not including that. Okay. All right. Let's do one more example. Okay. This time we have a spring, and we have a spring that is tied to a box and tied to another box, okay, like this. Okay, so let's again see if we can get all the forces over here. In fact, if you like, pause the video over here and try to draw out all the forces on this. Let's call that A and that B. And once you draw out the forces, ask yourself, what is it from where and on where? Okay. All right, so let me put them in. So hopefully you've done this yourself. If you haven't, pause the video right now, last chance, and give it a try, right? And see if you got this correct, right? So use the same 2 questions, and here we go. So let's start with this one. Okay, so what's it touching it? Well, this in contact with the spring over here, and that means it's causing. What does the spring do? It's pulling it, right? So it's trying to pull it up, and we have a special name for it. It's called a restoring force. So let's call it R, okay, or S for spring. It's up to you what you want to call it. What else is touching it? The rope over here, right? The string over here. What's this string trying to do? Which is it pushing it up or pulling it down, right? This spring is pulling it up, and I'm assuming this is sort of overextended. This thing is heavy, right? So it's extending the spring. So the spring is pulling it up. So this is the restoring force, and the rope is pulling it down here. So you have tension, and that's it. Okay, and of course you need to ask, what's not touching it yet, giving it a force? Well, gravity. So it's also, technically everything should start from the same point, but I'll just draw them slightly displaced so that we can actually see the arrows. So these are the 3 forces on this guy. For B, let me draw it separately out here, right? So that's B. What are the forces? Well, what's touching it? The string is touching it here. So we'll have a tension, okay? Again, try to avoid having the same symbol for two different things. Well, this one is pointing down, this one's pointing up, so they're different. Let's give a prime over there, and gravity. right? So there's nothing else touching it. So you move on to the next question. Gravity like on B as well. I'll just put a prime. I don't want to write out so much subscripts. Okay, but remember my second question is asked, see if you can identify, I won't write it out, but see if you can identify is from what and on what, right? Let's go through this. This is the force. So this is the force on B from Earth. This is the tension, which is the force on B from the string. This T is the force on A from the string. This G is the force on A from Earth. And this R is the force on A from the spring. Okay. All right. So yeah, there you go. Let me give you an exercise and see if you can do this on your own as well. If I have a pulley this time, right? Another very classic problem with two blocks, A and B, right? So in fact, let's draw three things, right? So let's call the pulley C as well. Can you draw the free body diagram on A, B, and also C? Okay, so assume actually, yeah, let's say the pulley is connected to the ceiling. Like this. So it's hung over here. It's a pulley, so you can move up and down. These things would, yeah, there's like a wheel. You can connect with a string and move them up and down. So what are all the forces on here? All right, give that a try, and we'll see you in the next video.